boy, similar solids. All right, in today's notes, we're going to talk about similar solids. In the previous unit, which was area, at the very end of that unit, we talked about similar figures and how there's these scale factors that relate them. Okay, and that's what this first sentence is going to refer to here. So this is reminding us back to the end of area. You have already seen that if the ratio of edge lengths of similar figures is a to b, then the ratio of the areas of the figures is going to be a squared to b squared. Okay, on one hand, that doesn't look too complicated because you just have an a to b and then you get an a squared to b squared. But we really need to understand what it means so that we can continue to move forward and talk about three-dimensional figures. Okay, so this first part, I'm going to show you another example of what we did in that unit to help kind of jog your memory of those things. Okay, here's an example of two rectangles that are similar to each other. The reason that they are similar is because there's a scale factor that relates any of the corresponding dimensions. For example, to go from the 2 to the 6, you multiply by 3, right? And if you take that same number, that 3, you can multiply this 3 by 3 and you get 9. So you have this scale factor of multiplying by 3. The weird thing is that same scale factor is not how you compare the two areas between the figures. See, if I calculate their areas, I got 2 times 3, which is going to give me 6. For the larger, if I multiply 6 by 9, I'm going to get 54. And I think you can see that it's obviously, like if you take 6 and you multiply it by 3, you're obviously not going to get a 54. However, let's divide these anyway and see what number relates them. So if we take 54 and we divide it by 6, you actually get 9. And what's interesting about that is that 9 is this number squared. And that's going to be true for any pair of similar figures that we have. If you do have a scale factor that relates all their sides, and that's what would make them similar, that scale factor to the second power is how you're going to compare their areas, okay? All right, in today's notes, what we're going to look at is how we take similar solids, three-dimensional figures that are related by a scale factor and how they compare to each other as volumes. Okay, so with that, let's go back to the notes and see what we have. If you have a single scale factor, some sort of a ratio that compares the side lengths of figures, then the areas are going to be compared as that thing squared. However you want to describe it, if it's a scale factor, if it's a ratio, it's going to be that thing squared. But then when you move into 3 dimensions, that comparison is actually going to get cubed, right? So if I can't do this with the rectangles, but if I had a rectangular prism and I investigated that shape, which we're going to do in a minute anyway, when we do that, you're going to see that the comparison, the scale factor is actually now raised to the 3rd power. Example number 1 is going to have us look at a rectangular prism with the dimensions of 14 inches, 4 inches, and 6 inches, and see what happens to the surface area, that's the total surface area, and the volume if all of those dimensions are multiplied by 2. Okay, to do all of these questions, well, all the questions that you're going to see in the notes today, I like to create these little tables. I don't know how perfect these are for actually teaching it, but for me, I think it gives me a concept of how to organize some of my thoughts. Okay, so on each of these tables, and you don't have to have everything labeled like as you get used to what I'm doing on this, but this is what it looks like right now. What I'm going to do is a comparison of the dimensions, whether it's like 1D, 2D, or 3D, versus the scale factor that we see in the problem. Okay, so 1D, above that I have a P, and that just stands for perimeter. 2D, that's going to be your area type problems, and then the big focus for today is really about 3D dimensions, which is going to be volume. Okay, now given the prompt, the scale factor that we're going to be using to change everything is going to be a 2. So I already got that one filled in here. Okay, but what's going to be interesting when we go through and we investigate everything here is that the scale factor for the area is not going to be a 2. Now, if you're paying attention to the rectangles, you probably could already figure out what the answer is, but it's going to be neat to see when it happens in the actual math. The volume, we really haven't done any examples of that yet, but you might be able to predict what the scale factor will be. Okay, so we got a scale factor at the beginning, which is a times 2. What's going to happen to the area? What's going to happen to the volume? Now, most of this stuff I've already got worked out for you, just so you didn't have to watch me write anything. Okay, this is going to be calculating the surface area without any dimension changes, just to see what we've actually got. Okay, so what I have here, I've got these products that are each going to be doubled up. So there's a 14 by 4. That would be the right face over here. But I'm going to multiply by 2 because there's another one. I've got the 6 by 4. That's going to come from the bottom, but then times 2 because you've also got the top. And the 6 by 14, that would be the front and the back, so times 2 for that. Okay, so if you add up all 6 sides, 2, 4, 6, if you add up all 6 sides as their areas are calculated, you get 328. Okay, next what I'm going to look at is what would be the surface area if we double all the numbers. If we change the 6 to a 12, we change the 4 to an 8, we change the 14 to a 28. Okay, so basically I have the same thing copied now, but what I've done is I've doubled all those numbers. So the 2's are still the 2's because that's just like left side, right side stuff. But the 14's became 28s, 4's became 8s, 6's became 12s. Okay, and I add all that up together and I get 1312. Okay, and that might, like with the size of the numbers here, you might not notice any like real comparison, but I mean, these are similar figures, right? It comes back to this idea that we do have similar figures. If I take the larger number, 1312, and I divide it by what it used to be when it was a smaller figure, the 328, I get back exactly 4, all right? Okay, so if I have a scale factor in 1 dimensions, which is a times 2, in the area, at least in this example, it's turning out to be a 4. That's a comparison of them. But that actually goes with what we look at here. If our scale factor is A to B, or ratio is A to B, then when you compare areas and surface areas and area, that's going to be an A squared to B squared. So if I have a scale factor of a 2, 1 to 2, I should get a 1 to 4 out of that one, and that's where this comes from. So this is actually just 2 squared. Okay, so then let's see what happens with the volume. By the way, volumes are much shorter calculations than the surface area. So if you notice that, yeah, that's true. The volumes are going to be such faster problems. Okay, so for the volume of the figure as it was, you just multiply the 6, the 4, and the 14, and you get 336. Okay, now we change them all, so we can change it to 12, an 8, and a 28. We double all of the numbers. I don't need that anymore. And you get 2688. Okay, so what I'm going to do is I'm going to take that larger number, 2,000, we're going to get somewhere to show. All right, 2688, and I'm going to divide it by 336. Okay, before I press enter, see if you can predict what it's going to be. Based off of everything else that was said about what we see going on over here. Did you think 8? Because it is 8, right? When you divide these, 8. Okay, in other words, when you change the dimensions by a factor of 2 for the figure, right, every measurement you take is now going to be twice as long. The area, when it gets calculated, the surface areas, are actually going to not double, but they're going to quadruple. It's going to become a 2 squared. That's your factor that compares it. Your volume gets magnified even more. It's going to be 2 cubed, 2 to the 3rd power, which means 8 times the volume. So when this guy, this figure here, becomes its larger version, 12 by 8 by 28, it would actually take 8 of the little ones to make the larger one. Example number 2. Before I actually start the problem, you should probably pause the video, go ahead and copy it, and give it a little bit of thought first, okay? All right, so example number 2, what's kind of interesting about this is you don't really know any of the dimensions of the figures. You're just told that you have 2 similar cylinders. You do get their surface areas, or the lateral surface areas that go along with them, but you don't know what the radius is, and you don't know what the height, and you don't know any of the like specific numbers. But here's your key things here, is you've got that word that says that they are similar. So there is this whole idea of a scale factor that relates them. Okay, and you'll see my little table here again. I've got my one-dimensional for perimeter, I've got my area stuff, and I got my volume. Okay, so what they did is they gave you the actual areas. they didn't give you any scale factors, but they gave you the areas. And if you take those two and you divide them, you can get that number. You can figure out what the scale factor is that relates the two of them. So let's see what that looks like. Okay, I'm going to take 1019, divide that by 425, and I get, make sure you can see that there. You get this awful looking number, right? There's nothing great about it. Okay, but I'm going to keep it in the calculator as I continue to move forward, so don't worry about all the rounding issues. Okay, but I am going to jot it down. Okay, so my scale factor that relates, it rounds off like that, but again, I'm keeping my calculator. The scale factor that relates the surface areas or the areas is going to be that number. What we have to do is then figure out if we have the volume in third dimension stuff, if you have the volume of the smaller figure, what would be the volume of the larger one? Okay, so what we're going to do is we're actually going to work backwards. We're going to move that direction to figure out what the scale factor is on a one-dimensional plane. And then once we have that number, we can just cube it, and it gives us a comparison for the volume. Okay, so I'm going to take that number that's in my calculator. Remember that this is the one-dimensional scale factor squared. So if I were to square root that number, it drops down to 1.548. Again, doesn't matter on the rounding because I'm going to keep it in here. Okay, so this, like compared to example number 1, is like the 2. This is going to be the 4, right? So this is 2. This would be like the 2 squared, and then I should get a 3 squared. So if I take that one-dimensional scale factor now and I cube it, it's going to give me the comparison for the volumes, which would be 3.713. Okay, now I'm keeping the number in the calculator so it all works out fine. All right, well, we've got this 1157. That's going to be the smaller cylinder. So you want to multiply that by our three-dimensional scale factor. And that will give you the volume of the larger one. So I just kept the number in the calculator, multiply that by 1157, and there it is. You get about 4,295, and we'll just say 0.5, and this would be centimeters cubed. Okay, so it's a bit of a tricky one here, but I think that these tables, if you get used to the idea of what I'm doing here, can be helpful. Whatever you've got here, this is going to be that number squared, and this is going to be that number cubed. That's the comparison. So if I gave you like a volume, like 2 volumes, and you found their scale factor, you could cube root it to get to here. Then you could also square it to get to the area. So there's a lot of ways you can move around with those numbers. All right, example number 3 is going to get us into what is called non-proportional changes. Now, technically, that doesn't even match the title of the notes because the title of the notes is about being proportional, and that, being similar is being proportional. What we're going to do here is look at how the surface area or the volume could be changing if you don't change the dimensions by the same amount. Okay, like in this particular problem, the cylinder, the height is going to get tripled. So it's going to go from 12 to 36, and then the radius is going to get doubled. So it's going to go 4 to 8. But you're not doubling both of them, and you're not tripling both of them. You're only going to, you can do different things. You're going to double, and then you're going to triple. All right, and the truth is, with most of these problems, you actually just have to do the full calculations to figure out what the comparison is. Okay, so all of this is going to be the surface area calculated with the figure as it is. So the formula for the cylinder, it's going to be 2 pi r squared. That's going to be 2 circles for the bottom and the top, plus 2 pi r times h. 2 pi r is the circumference multiplied by the height. That's going to give you the lateral surface area. Okay, so with everything plugged in, you're going to replace the r's with the 4's, replace the h with the 12. It's going to work out good to do everything in terms of pi here. So that's kind of showing up a little bit more in this unit. We should keep to it. That's going to be 16. 16 times 2 is 32, and then all of that calculates to 96. So then you can add these together as like terms, which is going to give you 128 pi. Okay, so I'm keeping it in terms of pi because, well, you'll see the numbers just work out better. All right, next, this is going to be the surface area calculated with the changes described. So the radius gets doubled, which is going to give you an 8, and the height is going to get tripled, which will give you 36. Okay, so then on to 64 multiplied by 2 is 128, and then all of that multiplied is 576. Both of these are in terms of pi, so again, like terms, you can add them together, which is going to give you 704 pi. Okay, and since both the previous and the new one are in terms of pi, what we can do is just divide the coefficients, the 704, divide that by 128. See if you can see that. And it gives you 5.5. Okay, when you divide, you get 5.5. And of course, when you divide, if you had the pi symbols in there, then the pi symbols will end up canceling out. So the surface area changes by, I should say, a factor of 5.5. It's not simply just a number, but it's the whole idea of how it's actually changing. Excuse the horrible handwriting there. The surface area is changing by a factor of 5.5. All right, what we're going to look at last is how the volume compares for the cylinder when that height was tripled and the radius was doubled. Like we saw in one of the previous problems, the volume calculations are going to be much shorter than the surface area ones, so that's a convenient thing here. The volume calculation for a cylinder is going to be pi r squared times h. That's the area of the circle multiplied by its height. With the regular numbers in there, you're going to have 4 for the radius, you're going to have 12 for the height, which is going to give you a total of 192 times pi. Again, I'm going to keep that in terms of pi. The volume, when everything is changed, you've got the doubled up radius. You also have the tripled height. That's going to turn out to be 2,304 pi. So if we divide these two together, and you can just leave off the pi symbol when you divide. And if you divide those, you're going to end up with 12, an even number of 12. All right, so the volume changes by a factor of 12. All right, now that one I think is a little bit more of value than looking at the surface area problems. See, one of the big differences is that when you do surface area type questions, you have a bunch of individual components that are being added together, okay? But in the volume, it's almost always just a product of a bunch of numbers. So if you look really close, the radius you see counts twice because it gets squared. So when you double the radius, you're going to introduce a factor of a 2 twice. For both of the times, the radius gets doubled once, but since it counts twice, then the doubling counts twice as well. And the height, when that changes by a 3, since the height only counts once in the equation, that factor gets involved once. So if you multiply all these extra numbers that show up in this one versus what we originally had, a 2, and now a 3, that product is actually 12. Okay, so usually the volume questions are the ones that you're gonna see as these non-proportional changes because it's an easy way to track all of the numbers throughout the whole calculation, whereas the surface area, it's a bit more difficult.